most of you rightly saw that the rate of change is, what is the rate of change? 1.5 no matter what time it is. So this is what a constant rate of change graph looks like. No matter how much time has gone by, it's 1.5. And then the number of gallons added will start at how many gallons? Start at 0. And then total number of gallons of the tub will start at 2. Okay, so very simple exercise here to point out that we're going to name these as have 3 different names for these types of graphs, okay? So this is a rate of change function, okay? So rate of change function, of course, it tracks the rate at which a quantity is changing. And so for this particular example, that rate of change was constant, okay? So this one up here in the upper right, we're going to call a net accumulation function. What does that do? That tracks how much change you had since whatever 0 was. So a net accumulation function is tracking the amount of change from a reference point. How much change from a reference point? So at that reference point, the amount or the amount of accumulation will be 0. Make sense? And then this last one we'll call a total accumulation function. So that's the total accumulation of some quantity, including a starting amount, if there is one. So do those titles make sense in terms of what we're doing? Okay. So things are nice and easy when you have a constant rate of change function, right? But so when do things get interesting and more challenging is when you have a changing rate function. When you have a changing rate function. So let's work through an example here. Or not just an example, this is going to be a big investigation here we're going to do. And so here is, any questions on the preliminary exercise or definitions? Any questions? All right, so function R sub v gives the rate of change of volume. So you can turn over if you want, but I actually have another worksheet for this. But gives the rate of change of volume of oil expelled per day by a rig that begins leaking at t equals 0 days. So at t equals 0 is when an oil rig begins to leak, okay? And then this is the rate of change. The rate of change of oil in meters cubed per day for the number of days since the leak began. Okay? So what do we mean? All right, so how about this? So can you imagine, we'll start with this question. Can you imagine a function v that would give the total accumulation of oil, not amount. So going with our definitions there. So can you imagine a function v that gives the total accumulation of oil expelled x days after the rig started to leak? So could you maybe just make a rough sketch of that? No numbers involved, but could you make a rough sketch of the total accumulation of oil expelled? And we'll assume that at time equals 0, the ocean was oil free, okay? So there was no oil in the ocean at t equals 0. So in this case, the net accumulation and the total accumulation are exactly the same. Does that make sense? So, starting with 0.
Straight line.
So lots of, I think almost all of you had something like this. And so the rate is highest at the beginning, so the amount of oil is shooting up faster, right? And then the rate of oil decreases. So you have a more gradual increase of oil in the ocean, and then the rate maybe increases a little bit at the end. Something like this, as a rough sketch. Okay. All right, so what is our endeavor? Our endeavor is so like we said, things are easy with a constant rate of change, but when you have a continually changing rate, getting this function from this function is a challenge. Okay, it's a challenge because the rate every moment the rate is different than it was before. Okay, so we are going to, that's kind of our goal. It's like, if we had this changing rate function, how could we get that thing that you were trying to sketch? But exactly, like how could we model that exactly? All right, so let's first talk about the rate of change function. So I have this statement here, r sub v of 0.7 equals 9.68. How does that relate to the graph? So I'm not asking you to define any values, but how does that statement relate to the graph that's above? Volunteer answer that. How does it relate to the displayed graph? That statement that RV, Ben?
So it's asking, at 7 days, 0.7 days, what is the rate of change of the volume expelled?
Okay.
And that's going to be 9.68.
Right, and how does that relate to the displayed graph?
Straight is the one we drew after?
No, the rate graph. How does that statement relate to what's the relationship between those two things? Shanley?
Wouldn't it just be a point?
A point. Right, so it's a point. It's a point on that graph. That exactly the point defined by what Ben said. At 0.7 days, the rate of change is 9.68. Okay, so that's a point on the graph. Okay? And then what does it mean in this context? Now, I'm not asking you to describe what 9.68 means, but what does it mean that at 0.7 days, the rate of change is 9.68?
Still increasing.
Okay, it's still increasing.
Even though the rate at which it's increasing is decreasing.
Okay. So 9.68 is a rate of change, right? So does it make sense to talk about at the instant of 0.7? Why not, Jessica?
Like a small,
Because it's, like a small interval of time around 0.7 that the rate at which the oil was leaking was 9.68.
Okay, so she said for a small interval, Jessica said for a small interval time around 0.7 that the oil is leaking at 9.68 meters cubed per day. And so we're considering that so in that perspective of it, what are we considering the 9.68 meters cubed per day? As a what kind of rate?
constant.
Yeah, so what we're saying is that at the moment, remember I talked about this last time, by a moment we mean a really small interval. So in that moment, a very small interval around 0.7 days, we're saying it's essentially a constant rate of 9.68. So that's what we mean by at 0.7, the rate of change is 9.68. Because you can't have rate of change without change, right? You can't have rate of change without at least a little bit of change. Yeah,
We get around that by like epsilon or plus or minus h, and then having that approach 0. Like we still need like an interval of some size.
Okay, so that right. So that's a more pure mathematical way. But if we're talking about we're really thinking about the oil leaking into the ocean, and we have this number 9.68 meters cubed per day, it only makes sense if we have some little change in time.
Even if it's just like a microsecond.
Right. Okay. So here's this is the actual rate graph for a moment around 0.7. Okay, so this is what, from 0.697 to 0.703. Okay, so it's 0.006 seconds. That's the moment. And here's the actual rate graph. But according to how we defined that 0.7 and 9.68, according to this ordered pair of 0.7, 9.68, what graph would we have? What graph would we have according to this way we defined r of 0.7 being 9.68? What would the graph be like? What's that? Horizontal, right? Horizontal at 9.68. So by taking that meaning of what does it mean at 0.78 that the rate of change is 9.68, the red is the actual, but we're really operating in the blue, right? We're really operating on this blue horizontal graph. Okay?
Is it like the average rate of change for that moment?
Nope, because we're taking this value that we got from 0.7.
Okay.
We're letting it be constant for just a little time around 0.7. So it's different than an average. Okay, it's different than average. Okay, so we say that the rate of change at the moment is a constant rate of change of 9.68. Okay, so I have a task for you, or a couple tasks for you, and this is the next. So this is the screen you're looking at right now. Is the hands-on activity.
Oh, wow.
Okay, so who's got an extra? Any more? Everyone's got one. Okay, so now we're going to put to work what we've been working on. Okay, so we've got this constant rate of change at 9.68 for this moment around 0.7. And so let's suppose, so I'm just giving you this, that at 0.7, the volume that's leaked into the ocean at 0.7 days is 13.15 meters cubed. Okay, so that's just, I'm giving you that. So under our assumptions that it's just for around 0.7 that the rate of change is essentially constant, if our goal was to find v of 0.7013, then what would dx be? What would dv be? And then let's find v of 0.7013 and illustrate it on the graph below. So I'm really looking for you to apply the principles we talked about. So don't go back to your thinking before this course. Use the things we talked about in the last 2 weeks, 3 weeks. Really apply those principles to answering these questions. Did these tasks feel like they related to what we've done?
Yes.
Okay, so Morgan, no. You're shaking your head about something else?
What?
You shook your head when I asked that question. Was it you're shaking your head to something else?
Yeah.
Okay. All right, so who wants to help me out with v of 0.7013? Let's see here. Alex, how did it go? So my goal in the end is to find v of 0.7013. So can you talk me through step by step or through the process of finding that? Well, I kind of gave you a clue there. So first, what are dx and dv for that? So what's dx if I'm after v of 0.7013? Okay, for dx, if I know what v of 0.7 is and I want v of 0.7013, that doesn't involve the rate of change yet. So Ron, what did you think? Ron, go ahead.
Well, the idea is right. So the change in x would be 0.001.
Okay. And you got that?
I did the whole thing with 0.003. The process is the same.
Okay, so are we clear on that? The implied change in x there would be the change in our independent variable, which is the 0.0013. Okay, and then Ron, from there, how do we get dv?
So if we know the change in x and we know the constant rate of change, we're assuming for that interval, then the change in v, so the dv would be 9.68 times the change in x.
Exactly, right? This is what defines constant rate of change. For any change in the independent variable, our change in the dependent is that constant rate times the change in the independent. And what did you guys get for a number for that? 0.0. One more time? 1, 2, 3? Yeah. Are we in agreement on that? And then, so we'll just stay at that table. So Daphne, can you take over from there? What from there? Okay, let's make sure we're on the same page. What is 9.68 times 0.0013?
Well, 0.0126.
3 decimal places. 3 decimal places.
0.0126.
That's
Yeah, 258.
That's fine. That's good. All right. So where from here, Daphne?
I was choosing 2, 3 in my mind. So I said 2, 3.
Uh-huh. Right? Right. Perfect. And how about that? Is that right to 3 decimal places? That's meters cubed. Okay, so let's illustrate that. I want to illustrate that. So how do I illustrate? Peter, I'm going to illustrate that whole situation, that whole thing we just went through down here. What should I draw? What should I do?
You should plot your point, your initial point.
Okay.
0.7 and the 13.15.
Very good. Okay.
And then go over to 0.7013, or estimated, I guess.
0.013. So it's about a third of the way from here to here. Is that about there? And that represents dx. Okay.
And then you start from the beginning, or do I know that point already?
This point.
Or like the actual point? Do I know the 13.163 right now?
Yeah.
So then just plot that upward, your next point.
A grape came rolling my way.
M&M.
Oh, it's an M&M. It looks like a grape. Sorry, Peter. So what now?
I mean, you could plot your next point if you wanted to.
Okay.
Which would be from that point upwards to the 13.163.
And so yeah, and what came before? What came?
Also, yeah, to be honest, I know that.
Yeah.
And I just put
No, what allowed us to get that point?
just like assuming it was some arbitrary y value, and then I don't know what he wants. I understand.
But you just didn't make this number up. Where did it come from?
It came from our change in y.
Right. So that's what's next.
What do you- that's what I was doing, wasn't it?
No, you just kept asking. Can I just go to that point? Can I just go to that point? Can I... Yeah. So the dv is what gets us that point, right? The dv is what gets us that point. So is that about there? And that dv is the 9.68 times 0.0013, or the point. Okay, and then
Oh, what do you mean? Where were we at?
so and then that change in volume we know then results in the final volume of 13.163, which is V of 0.7013. Okay, so we won't do the other one. The other one is going to send us what? What is dx? 0.002, and then the dv turns out to be
169.
dv
Oh, DV.
0.019, and then yeah, so it's gonna take us out like further here, and then dv is larger, something like that. Okay, and so then we could think of dx as actually a variable. So I gave you, we had two like static values of dx for which we calculated the final volume, but we could think of what dx varying from dx equals 0 right there to dx equals 0.002. So right there, dx equals 0. Agree? Here, dx equals 0.002. So if we imagine dx varying between values of 0 to 0.002, then what results would we get? What result would we get imagining that dx was varying in terms of volume of expelled oil into the ocean?
dV would be changing as well.
What's that?
dV would be changing.
dV would
as
be
well.
changing, and so then what would the result be for volume? What's that? Someone said it? Yeah, right. So we get what do we get? If we let dx vary, then we get what? Every point. Right? We get, instead of just those 2 points, we get every single point from there to there. Should have done it in blue. But I can go over the top. Right? Imagine that dx varies between 0 and 0.002. Gets us all these. Is it getting better or worse? That's not bad. That's not bad. Anyway, yeah, so what we get all the points. We get all the points for times from 0.7 to 0.702 days. If we imagine dx varying from 0 to 0.002. Okay, any questions on this? So this is like a little piece. So what we said was we're trying to recover this entire volume graph. So we just got just a tiny little piece of it, right? A tiny little piece of it for the moment of 0.7 days. For the moment of 0.7 days, we came up with a little tiny bit of that volume function for 0.002 days, right? So it'll take us a long time to build the whole function at this rate, right? Okay, but still, this principle. This is the guts of how we're going to build the v function, right? At any given moment, we assume a constant rate, and then using that constant rate, we can get these different correspondence points of actual total accumulation and time. Questions? Okay, so let's see that same thing from a different perspective. Turn over your paper. Yeah, please.
Okay, so like, we assume the blue line, but we know it's the red line. So we know that that's not actually how it is.
Okay, good. So she's pointing out that we assumed the rate was really this slightly changing rate, and we assumed it to be constant. And so is your point that then the resulting kind of straight line graph isn't really perfectly accurate?
Yeah.
What do you guys think about that?
Yeah.
They're not.
So
Okay.
how do we like decide
Okay.
how far we
Okay. So from an exact standpoint, that's true. But what? But what?
For the necessary things,
What's that?
for the necessary anything we actually need it for, it works. It's impetus incorrect where it wouldn't really matter.
Okay, so
Does that make sense?
why doesn't it? Why? Okay. So you're saying,
It's off by very little.
okay. Why is it off by so it's not exactly correct according to the red rate of change graph, but what is the error involved and why? So he's saying if your error is virtually none. Is that what you're saying?
Yeah.
And why is the error so small?
I was going to say just because we're in such a small decimal that it doesn't really change the error, like you said, is so small that it doesn't, we're in such small increments, it doesn't
Right.
change the problem.
Right. So the width of our moment here is 0.006 days, which is a lot of seconds maybe, but in terms of days, 0.006 days is very, very small compared to 1 day.
Right.
Yeah.
I guess I'm just asking, how do we decide how far we can take that?
Size of what?
The interval?
Size of that.
Yeah, the interval. Like, how do we decide?
What is small enough?
Yeah. Like, because we obviously can't.
So if we had the volume graph, would we be satisfied that if we zoomed in as far as to 0.006 days a moment, would that graph be essentially straight? or would we still see a curve on that? Does that make sense? So if we kind of imagine, if we did have the volume graph, I mean, that's what we're trying to produce in the end, but if we did have that, and we zoomed in this far to this amount of precision, how would that graph appear? If that graph appears essentially straight, then our assumption is fine, that this is a constant rate of change, right? Because a straight total accumulation graph would be constant. But if that would still appear curved in that small of a moment, then we have maybe assumed wrongly.
So the answer is depends.
What's that?
So is the answer to how far we can just take it, it depends. Like,
Yeah.
like for example, like where the rate of change changes, like where it starts going positive more as we're getting
Increasing again? Mm-hmm.
Right. So like at that point we would have to maybe do it differently.
No, but you gotta remember, this is 0.003 days. I mean, so it's like, you can't even see how big that interval is on this graph.
Okay.
So if you picked any time in days, you could make that small of an interval and assume a constant rate. It wouldn't make a difference here or here or here, because it's still the same microscopic or minuscule.
I guess I just want to know exactly how far we can take that.
Yeah. All you need to do is have a small enough interval. Small enough so that your accumulation graph would be essentially linear. And then you can assume a constant rate of change. Okay. All right. Any other questions? I'm happy to.
So if we have to recreate this, will you tell us like the interval you want?
It's not the point. It's not the point. A moment is small enough to be linear. So yeah. This is about understanding ideas. Don't worry about that. Just understand the idea of it. Okay? Understand the idea. Okay. Another question? Ask. No, you guys have a question?
No, we're just going over it.
Okay, you guys good?
Yeah.
Everyone good? All right. Okay, so now, taking a kind of different perspective, same goal, different perspective. Let's use really big moments. Okay, let's use, instead of a really teeny moment, let's use really big moments, and assume constant rates for large moments. So now, to Morgan's point, this will be really inaccurate. Okay, this will be really inaccurate, but it still is about the idea of what's going on. Okay, small moments gives us accuracy, like the previous slide. But now if we use really big moments, inaccurate, but we need to make more progress than just one little moment at a time. Okay, so here's what we're going to do. We're going to do moments. We're going to do moments. Okay, hold on. Do I have your attention? We're going to have moments of 0.5 days. And in each 0.5 days, we're going to assume a constant rate of change. And so for the first 0.5 days, don't draw anything yet. Don't write anything yet. For the first 0.5 days, what would be a good assumption for the constant rate of change over those first 0.5 days? What would you say? How about 10? How about 10 meters cubed per day for the first 0.5 days? Good assumption? No, why not? Why is that bad? Okay. What do you mean? Okay, so here's what I'm asking. How about this for a constant rate for the first? Why not? Why is that not a good assumption for a constant rate for the first 0.5 days? It's not about being... What's wrong with that rate? It's way too low. The rate is way too low. What about 40? Too high. So, give me a constant rate that might be a reasonable constant rate for this first 0.5 days. 18, 20, okay? Still don't draw anything yet. So I heard 18. What about 18? it's most of the interval is still lower, right? So if we're trying to reproduce this graph the best we could, we can do better. What another suggestion?
15.
Here's 25. What about from 0.5 to 1? Someone said 10, 8. These are good. These are fine. Both of these. 9, 10, 8, something like that. Okay, what about from 1 to 1.5? 5, 4, something like that. Okay, 1.5 to 2? 7, 6, 8, something like that. Okay, but the problem with this is, so that's fine. We're doing our best, right? For these large moments, we're doing our best to get constant rates to match this graph. But the problem is, there's no rhyme or reason to it. It's like we got to go through each interval and pick and laugh every time, and So we want something more systematic, right? Something more systematic. So what if we, even though it would be much less accurate than what we just did, what if we took the actual rate at the left side of every interval? So that's the one you're going to sketch. So for intervals of 0.5, you're going to pick constant rates that are equal to the real rate at the left side of each interval. Can you draw that? Can you draw that?
I know.
So for each interval of 0.5, a constant rate equal to the actual rate at the left side of the interval. Let's see, I might.
Yes, trust me. Yes.
Did you get something like this?
Yes.
Okay. So less accurate than the eyeballing thing. I mean, look at the rate. The first constant rate is way too high, the whole interval, right? It is too high because the rate is always lower than that. But at least this is systematic. So with this, we can actually now write out what this. So this, if the real rate function is r sub v, then we're going to call this pretend rate function or approximate rate function. Or simulated rate function, we're going to call that r. Now I want you to write the definition of r, and I want this function exactly. I don't want estimates. I want this function represented exactly, what you just did. Now I want you to scratch off the... So I'll put it on here, because you guys all got it.
I doubt it. I witnessed that.
Yeah.
Well, I mean, so is that part like
Okay, so one question we could have about this, one question we might have about this is, in terms of the endpoints. So how should we do the less than or less than or equal to, or how? So I've suggested a certain way here, but should I have it the other way? Okay, so if you have a conviction, what's your justification?
Well, you said it was left.
What's that, Jacob?
Kendall's got it.
Kendall, go ahead.
Okay, sure. So on the first one, because I did mine opposite, I have 0 less than or equal to x, less than or equal to, not less than or equal to
Okay.
0.5. Then on the next line, it's 0.5 less
Right.
than or equal to x. Because there's a jump on the same x value on 0.5, and it obviously can't be equal to the y value cannot be the same for both. The y value at the end of the first segment cannot be the same as the y value at the start
Okay.
of the second segment.
No, I haven't violated that, right? Because I just do strictly less than there, and that's not equal to. So the question is,
Wait, so what is your question?
so
Why did we left?
yeah, so you're putting your less than or equal to's here on the left side, and the less than's on the right.
And that goes back to the way I drew the picture because I drew a point at the start of each segment,
Uh-huh.
not a point at the end of the segment.
Okay.
So that would be like filled in hole equal to.
Okay. Josh.
One thing is also just on the left hand, on the left hand side, or it goes equal to the left hand side there. It goes really fast more because you're saying so if we change the rate
Okay.
instead of next to that point.
Okay.
Very similar. That the starting point of each interval. So when it starts at 0, it goes up to 0.5. The other one starts at 1.5, goes up until 1. The next one starts at 1. So
Okay. So you all agree that I should change mine.
No.
Okay. So I'm not going to do it, but because I don't want to take the time, because I want to see if we can do a sub x. So now a sub x is resulting accumulation resulting from this rate function. So can we build that? And I encourage you to reflect on principles we've learned in this class. Principles, things we've learned in this class. Can you do it? So,
So starting to this one, we were just doing this.
okay, so my time management has been poor today in class because I have to show you this assignment and we didn't get to finish this. So finishing this AX function, you want to think about that and finish that for a little bit of written homework. Here's the next GC file we're going to do. So this is based on what we did in class today. So you've got the rate function. So you're gonna here's that rate function, which is modeling the rate of change of the oil. To get a subscript, so you can make variables with subscripts. And to do that, you hit Control L. So if I do R, then Control L, it allows me to add a subscript, and now that whole thing together is a variable or parameter, and so I use that as the name of my function, R sub b. There it is. Okay? So dx is, in all your command lines, you want to use dx to mean dx, but that's going to be the value of n in the slider. So I can push play, and you see what's happening here. It's showing a changing dx as it goes. Okay. So a then, if I change a right now is showing this particular number of days. So so let me leave a as it is. In the right-hand graph, to open up a second viewing window, have we done that yet? Apostrophes. Y apostrophe, X apostrophe will open up a second viewing window. So here it is. So as in this particular interval, as X changes, according to that as dx changes or x changes. Then we have the corresponding kind of animation over here. In yours, so I've got a bunch of question marks. In yours, you're going to be actually replacing these question marks with the appropriate symbols. Okay? So you're going to replace, there's 2 on this side, and there's 6 on this side. So when you build it, you're going to replace the question marks with appropriate symbols. Okay? And so notice what's happening here for this rate around 20. If I change A, say if I make it more like 1.5 here in the middle, go back a little bit so you can see it. So do you see how the image then, what, a lower rate of change, right? And that changes what happens here.
Does that mean you want the second set of question marks to change as points? Like you want it to say 10 something, 5 something?
Nope.
No.
This is all these are symbolic. You could never do that, right? You can't. The symbols have to be static. They can change. What's that?
I just
Yeah.
thought.
No. Okay. So I will get further explanation on this, but this is what we're working on for Tuesday. Okay. Continuing my explanation from about this assignment due Tuesday. Okay, so we got our function, and this is that the rule that models the rate of change of volume of oil coming into the ocean. And remember to get us, if you want to define a variable or a parameter or a function name and use a subscript, you can use Control L. And it's really important with V that you make sure it's an uppercase V. Okay, if you use a lowercase v, that's reserved as a parameter for surfaces and 3D stuff. So if you use lowercase v, it will mess things up. Make sure you use uppercase V for this subscript. Okay, and A is the number of days, the start of this kind of moment that we're highlighting here. And so A is the number of days at the start of the moment. And then we're going to use the n slider to animate dx. But in your lines, you want to use dx, so it has the symbolic meaning that you want in all that mathematics here that's unseen, right? Unseen in these lines behind the screen. You want to use that dx. But here I'm making sure that dx is equal to n so that we can animate dx with the n slider. Okay, and so what we got? We're going to graph the rate function. We're going to, according to some starting time A, we're going to graph a moment of 0.5 days. Okay, so this moment is 0.5 days. And we're going to illustrate a constant rate of change equal to the rate at the beginning of that moment, that 0.5 days. And then we want to show that animated, we want to show the x increasing from that starting value of days through the moment. Okay, and so we want this vertical line, we want this point on our constant rate, kind of simulated part of the pretend rate function, and then we want these down here showing the appropriate symbols. So you're going to replace these question marks with appropriate symbols, and those will be, you can't have values that change because you're going to be using the symbol command. And so that symbol is just going to always stay the same. Okay, and so then over here, we're going to show a little bit of this increase in volume according to this constant rate. Okay, so you're going to build this animation over here, and remember the second window is going to use Y apostrophe and X apostrophe. We'll open up this second window, and as we traverse through this constant rate, it's going to show the volume increasing at that constant rate. Okay. Likewise, over here, you're going to fill in all these question marks with the appropriate symbols or expressions. They won't be values, but they will be the appropriate symbols or expressions that would define these two ordered pairs, and what this horizontal bar represents, and this vertical bar, what it represents. Okay. And now notice I've turned off the axes. If you see here in the graph, I've turned these off. Why? Because we would need to know, to have this exactly right, we would need to know how much volume of oil has expelled up to that point. And we don't know that, right? So we're starting at some arbitrary time and just taking it from there. So we don't know how much oil is expelled before. So this, for our purposes in this animation, this axis having this scaled, we don't want to show that scale. Now that being said, we do want the mathematics to be correct according to this rate and this time. So if you turn on the, or down here you can turn on the axes. So I'm going to draw axes. And now I'm showing the window that you want to use. So if you use this particular window with the x-axis scaled this way, which is the same as our rate graph, and if you have the y-axis scaled here as 5, 10, 15, 20, then when you do the math right, using the rate properly, you'll be able to, it'll be a nice view of this triangle animation. Okay, so you want to set your, do the math right in terms of the rate and building this volume, little part of the volume function, but set the scale to 5, 10, 15, 20. And so then what happens is we're always going to start at 3 on this scale because we don't know what that value is. We don't know what the starting for a number of days. We don't know because we're just kind of ignoring all the rate of change before, and we don't know, so we're always going to start at 3. Okay, so now I'll go back to, so I'll leave that up for now. So if you change A, then that changes the starting time for this 0.5 day interval, and the corresponding animation should change according to how the rate changes. So if I come down here to something in the middle like 1 or 1.5 where the rate is much lower, notice that that's reflected in the triangle animation, lower rate of change. And then this is only going to go up to 2.5, right? So the last one is at 2.5. And the associated rate of change reflected correctly, properly in this animation over here of the volume and growing, okay? So notice that no matter where I start A, that triangle always has a height of y equals 3 over here. I just picked that because it was away from the x-axis, but gave us a lot of room up here for this triangle to be displayed. So no matter how I choose A over here, it's always going to be, this horizontal line will always be graphed at 3, which has 3 has no meaning to the values, the rate of change, the volume. It's just a place, it's a place to start, okay? It's a place to start. That's why, because 3 has no meaning, the scale really has no meaning in terms of where we're starting. So then we're going to come here and turn it off. And we want to have just our own axes that we've created with GC, with command lines, and without the scale. Now if you wanted to add the time scale, that would be totally appropriate, right? So if you wanted to take this time scale and reproduce it manually along there, that would be great. But we just want to leave that volume scale off because we don't know the previous amount of oil expelled. We don't know what this Y value is. So it's always going to start at this level right here, which is arbitrarily y equals 3. I think I've covered everything there. Again, this is, so the great thing about this little project is in order to create this stuff, you need to know the mathematics that we're talking about in this class. And you're just using all these constant rate of change principles to build this animation. Don't hesitate to email me if you have any questions. If you come across things and you feel like I haven't covered it in terms of GC, don't hesitate to ask. Send me an email. But I think you should be able to do a lot of it with what I've given you here. But great exercise. I think it's the right challenge for where we're at. Hope you enjoy it. Good luck.